you're designing a CPU, and you want to make it go faster. So you get a bright idea. Let's install a turbo cache. Did it make a difference? You're not sure. What you need is a benchmark, one that exercises just the cache so that you can tell how much of a difference your change made. In general, what you need is a suite of benchmarks, one for each aspect of performance that you care about. The problem is that you have many candidates to choose from, and we need to figure out how to pick the best k-subset of them. To find out, we wrote our own. That way we could understand their performance. They exercise a particular feature in a few different ways to give us redundancy. They exercise each of the different features, and some of them even exercise multiple features. The first approach we took is to try and represent the full data set with a subset. So we tried k-means. You run k-means clustering over the full data set, and you pick the subset that is closest to the cluster means. If you do that, you come up with a data set that has a bit of overlap but does touch all of the different dimensions. If you want to be a little more clever, you could try a Gaussian mixture model. Pick a k-subset, model it with a Gaussian mixture model, and ask, how likely is it that the full data set came from this model? You pick the subset that is most likely to produce the full data set. Again, you get a bit of overlap, but it does touch different dimensions. A different approach entirely is to maximize the difference within the subset without worrying about the full data set. So imagine you pick a subset and you run PCA, and you ask how many PCA dimensions does it take to account for 90% of the variability. We count that as the dimensionality. You also measure the distance. How extreme was the benchmark along the different axes? If you maximize those two scores, you come up with a data set that's highly orthogonal with minimal overlap. If you want to be clever again, we could try Gaussian mixture models. This time, you take a k-subset and you throw one of the benchmarks out, model the remainder with a Gaussian mixture model, and ask, how likely is it that the one we left out was reproduced from the remainder? You pick the subset where it's least likely that the remaining benchmarks can produce any of the outliers. Again, if you do this, you come up with the exact same distribution, showing again that often it's the simplest case that does best. The last step is to see if our approach is generalized to the real world. So we looked at the NAS parallel benchmarks and ran our algorithms. Indeed, we found highly orthogonal benchmarks that push the dimensionality. So, with a real benchmark suite in hand, our engineers are able to find out that instead of a turbo cache, they should have installed a turbo branch predictor.